Hey guys, hello everyone and welcome to the channel. Now this particular video is about Monday MCQ series, and since I am resuming the series, many of you have asked me to do so because like many of you wanted to solve chapter wise questions, right? And I also thought that it's a good practice that because since the exam is getting postponed again and again, so we have a lot of time to practice new questions, right? So this particular series will help you to solve questions from a specific topic, and I'll be making around 15 to 20 question on a particular certainly topic, right? So the questions and all I have already discussed in my past videos, that where I'm going to post the questions. So the questions will be posted on the Telegram channel. So if you have not subscribed to the channel, go to the Telegram and just join the channel. Okay, the link are given in the description of this particular video. For this particular channel, you will always get, in every week you will get a new topic, Monday MCQ questions on that, and the questions will be published on Monday. You can practice those questions up till the next few days, and the solution will be uploaded by the end of the week. Okay, so that's how this will work, and that's how it has been working. So those who have not subscribed to the channel, subscribe to the channel. You'll be getting some very good stuff for your preparation of CSIR-NET exam. Also those who are new, who want detailed topics and all, so for them also I am making other series, right? So this is for those who want to practice questions. So enjoy the video, watch it till the end, and do give it a like if you like this particular video. If you are new to this channel, if you have not subscribed it yet, subscribe to the channel. So let's get straight into the video. So yeah, today's topic is inorganic spectroscopy. The questions were posted back on the Monday, and now let's talk about the questions and let's see how to solve them. So the first question over here is about your Mossbauer spectroscopy. It says that if the Mossbauer spectrum of FeCO5 is recorded in the presence of magnetic field, the original spectrum with the two lines changes into one width. So in order to solve this particular question, I will explain it how to do. But I will recommend you one thing, that I'll be posting link over here in the I button. You can click on this link to watch my video on Mossbauer spectroscopy. Okay, it's one of the highest watched video on my channel, and like I have explained each and everything about your Mossbauer spectroscopy in that particular video. So every question which has been asked in this particular like in this particular quiz, or anywhere, if you will see in your CSIR or in your GATE exam, you will find that the questions are asked from that particular video itself. So it's a very important video, especially for all the aspirants who are preparing for the exam. So it's highly recommended that you should watch that particular video. Now coming back to the question, it says that the Mossbauer spectrum of this iron complex, that is FeCO5, when it is recorded in the presence of a magnetic field, the original spectrum with two lines changes to one width. Okay, so they are asking that into which it is going to change. So let's try to solve this and try to understand. Now when we talk about iron, iron has two states, in the ground state and in the excited state, right? So the ground state has I value of plus minus half, and the excited state has I value of plus minus 3 by 2. So that's what we have. Now generally when the normal splitting happens, it will split up into two energy states. I will just show you here. So this 3 by 2 splits up into two states, one with I value of plus minus half and one with I value of plus minus 3 by 2. So these are the two states which will be formed, and the ground state remains unsplitted, so it remains as it is. These are all because of the magnetic quadrupole moment and all. So that is plus minus half. Now the transitions, if you will see, so one of the transition is possible from minus half to plus minus half, and the other one is possible from plus minus half to plus minus 3 by 2. So two lines which you will get generally, okay, in the absence of some external magnetic field. Now once you put the external magnetic field, that is called as your Z-man effect, okay, that is called as your Z-man effect, and that I have explained very clearly in my videos. So on the Mossbauer spectroscopy. So if you have watched that, you will be able to understand it. So according to this Z-man effect, this 4 energy state which will comprised of I value of 3 by 2, that is going to split up completely, and it's going to split into 4 energy states. Okay, this is going to split up into 4 energy states, and the I values are like from plus 3 by 2, then I is equals to plus half, then I is equals to minus half, and I is equals to minus 3 by 2. Similarly, your ground state will also split up because you are applying external magnetic field, so all the degeneracy, all the degenerate energy levels are going to split up. So that's plus half and minus half. So the number of transitions which will be possible will be from your plus half to plus 3 by 2, then plus half to plus half, and then plus half to minus half. Okay, because you know that delta I should be either 0 or plus minus 1. So these are the 3 sets of transition. The other 3 sets will be from starting from your minus half. So it will go from minus half to plus half, minus half to minus half, and minus half to minus 3 by 2. So these will be the other 3 set of transitions. So total 6 lines you will get in this. So 6 transitions, and I have also discussed about the intensity of these lines. 6 lines will be in the ratio of, so these 6 lines will be in the ratio of 3 is to 2 is to 1 is to 1 is to 2 is to 3. Okay, these are all the things I have discussed in detail on my particular video on the Mosfet Spectroscopy. So here the correct answer has to be option number D, which says that it splits into 6 lines. Alright, so this is the correct answer for this. Talking about the next question, which says that the total number of fine and hyperfine EPR lines expected for octahedral high spin manganese 2 complex are. Okay, so you have to deal with, first of all, you have to talk about the fine lines and the hyperfine lines. Now the fine line for one or for a single unpaired electron is 1. Okay, in manganese, since it's a high spin manganese plus 2 complex, okay, and that too it's a high spin, so obviously it's a D5 complex, right, and it has 5 unpaired electrons. So all these unpaired electrons are going to cause the fine lines. Okay, so the fine lines will be caused because of the unpaired electrons. Now we have 5 unpaired electrons, so 5 fine lines. So fine lines will be 5. That means you can cancel out option 3 as well as option 4. Okay, so you are left out with option B or C. Now 5, remember this thing, that fine lines will be equal to the number of unpaired electrons. Talking about the next thing, that is hyperfine lines. So for that we have to apply the formula. What is the formula? The formula says that it should be 2Ni plus 1. That's the formula, right? Now if you put the I value of manganese, that is 5 by 2. So how many manganese are there in the complex? So there is just 1 manganese in the complex, right? So you have to put 1 over here and then 5 by 2 and plus 1. Once you solve this 2 and this 2 will get cancelled out. 5 plus 1 you will get 6. So 6 lines you will get because of 1 unpaired electron. Now since you have 5 unpaired electron, so total hyperfine lines, okay, hyperfine lines will be product of your unpaired electrons multiplied by the value which you get it from here. So 5 into 6 is going to give you 30. So overall you will get 30 lines. The correct answer for this question will be your option number C. So 5 fine lines and 30 hyperfine lines. Remember this, that to find out the fine lines you just have to look upon the number of unpaired electrons. To find out hyperfine lines you have to multiply the number of unpaired electrons with the value which you will get from this formula, that is 2Ni plus 1. Alright, let's go to the next question then. The next one says that the number of lines exhibited by high resolution EPR spectrum of the species Cu, this is a copper complex, ethylene diamine, hold twice 2 plus. Okay, the nuclear spin of copper is given to us as 3 by 2. For nitrogen it's given 1. We have to draw it in order to understand. Alright, so this is how your complex will look like. Copper is in plus 2 oxidation state, that means it's a D9 species. D9 means, and if you fill this D9 species, you will get 1 unpaired electron. Okay, you just get 1 unpaired electron. So that means what? The number of fine lines will be just 1 from the copper. Now talking about that, who is going to split that up further? So nitrogen is going to split that up, right? First of all, because of the copper, it will split. So you have to use the formula 2Ni plus 1, and here I am putting the I value of copper multiplied by 2Ni and then nitrogen, because after copper nitrogen is present who is going to split it further, okay, and plus 1. Now do these hydrogen participate in splitting these hydrogens? Okay, will they participate in splitting? So no, they will not participate in splitting according to the Dragos rule. The Dragos rule says that if a particular atom which is EPR active or if atom is EPR active and if it contains hydrogen, let's say if the hydrogens are present on EPR active atom, then those hydrogen will not participate in splitting. So although all these nitrogens are going to participate in splitting, but the hydrogens will not. Alright, so these hydrogen will not participate in splitting. So just your copper will split and then the nitrogen will split. Now the question arises that whether these particular H are going to participate in splitting or not. So just to make you guys understand, it's this. Okay, you have copper, then you have nitrogen. With nitrogen you have hydrogen attached. With nitrogen you have carbon, and then two hydrogens are attached like this. Okay, this is everywhere. Like everywhere you have this. Now you can see that this hydrogen is actually 1, 2 and 3 bonds away from this copper. Okay, so if something is 3 or more than 3 bond away from the central atom, then in that particular case it does not participate in splitting. So that means when you are going to form the final answer of finding out the number of splitting, so you just have to put the values over here. So 2 into, how many nitrogen do I have? I have 4 nitrogen. So 2 into 4, I value of nitrogen, first of all we'll put we are putting it over here for our copper. Okay, now we have just one copper, so 1 over here. For that, I value of copper was given to us as 5 by 2. No, it was given to us as 3 by 2. Okay, so let's put 3 by 2 over here and plus 1. This is what we'll get from copper. The next part is from nitrogen, so it will be 2 into, we have 4 nitrogen and the I value of nitrogen is 1 and plus 1. So when you solve this, you will get 4 multiplied by 4 2 times is 9 plus 4 2 times is 8 plus 1 9. So you will get 9. So overall you will get 36 lines. Okay, so you will get 36 lines in the case of your particular complex. So answer comes out to be your 36 as the correct answer. I hope this is pretty much clear to you. Talking about the next question, which says that in the IR spectrum of para-nitrophenyl acetate, the carbonyl absorption band appears at. Okay, so where does your carbonyl absorption band appears? So in order to answer this particular question, you need to understand that how your para-nitrophenyl acetate looks like. Okay, so let me just show you that. So generally, like a phenyl acetate is this, that is you have a benzene ring, then you have O, C double bond O, and then you have CH3, right? So you have this as acetate group, this is your phenyl ring, and para-nitro means you will be having nitro group over there. Okay, now talking about the carbonyl like frequency, that's what it's been asked. Now the carbonyl stretching for your aliphatic esters, okay, for your aliphatic esters, it is going to be like for aliphatic esters, it's around 1750 to 1735 centimeters. Okay, that's the range for your aliphatic esters. Okay, the carbonyl frequency. Then you know that the carbonyl conjugated to the aromatic ring gives you peak at a little lower value. Okay, so carbonyl conjugated to benzene ring, although we don't have that over here, so we don't have to worry about it. But yeah, if you have an aliphatic ester and the oxygen is attached to the benzene ring or to the aromatic ring, which will reduce obviously the oxygen will be in resonance with this particular group, so the conjugation will be reduced in the side of your carbonyl band. Okay, so for the esters, if your oxygen is conjugated with the alkene or with aromatic ring, okay, so for esters, if your oxygen is conjugated with alkene, okay, or with some aromatic ring, in that particular case, what happens that your frequency decreases and it goes up to 17. Sorry, the frequency increases because this lone pair of oxygen will no further be in that much resonance with the carbonyl bond. Okay, so they will be also in resonance with the benzene ring. So that's why it happens. So the range goes like 1765 to 1760 centimeter inverse. That's the range. Okay, that is the range. But here you can see that you have nitro group as well. Now this particular nitro group has a particular effect on this whole molecule, and that particular effect is minus R effect of this this nitro group. So because of this, the frequency, basically you will see that the value for your para-nitrophenyl acetate goes around 1765 centimeter inverse, okay, because of the minus R effect. So if you look upon the options, so you will see that the value which is close to this 1765 centimeter inverse is only option number D, which is 1760 centimeter inverse. So we have to deal with this value itself, okay, although it has to be 1765 or quite close to that. So that's the correct answer for this particular question. Alright, let's talk about the next question now. The next one says that the recoil energy of the Mossbauer nuclide of mass 139 AMU is 2.5 mega electron volt. The energy emitted by the nucleus in the kilo electron volt is. So this particular question is totally formula based and it's just based upon the calculation. Okay, so let me just solve it for you and let me explain you how it will be done. So the recoil energy, in the terms of your electron volts is given by this. It is like 536 energy of your gamma radiation square divided by m. M should be your mass, and this value will come out in your electron volts. Okay, this is the formula to calculate recoil energy in terms of electron volt. Now, since in the given question recoil energy is already given to us as 2.5 into 10 to the power 6, and here on the other side it will be 536, and energy of the gamma radiation is what you have to determine, divided by the mass. Mass is given to us as 139 AMU. So you have to convert AMU into electron volts because everything has to be in electron volts over here, right? So that will be that you have to multiply with 931.5 in order to convert AMU into electron volt. Now E gamma square, which you have to calculate, will be equal to 2.5 multiplied by 139 multiplied by 931.5 and divided by 536, and so this is what you will get. And if you just have to calculate the final answer, this will be just under root of whole bunch of these things. So 2.5 multiplied by 139 multiplied by 931.5 and divided by 536. So this is going to come in the terms of your electron volts. When you will solve this and calculate this all, okay, so 10 to the power 6 is also there. So when you will solve all this, you will get 24.57 into 10 to the power 3 electron volts. Or if you have to express this in the terms of kilo electron volt, it will be 24.57 kilo electron volt. So this is going to be your final answer. Alright. So if you look upon the options given, so the closest option is your option number D. That is going to be the correct option for this question. Alright. Now let's talk about question number 6 over here. It says that the number of EPR signals observed in octahedral nickel plus 2 complex. Now nickel in plus 2 complex is going to have a D8 configuration, and in the octahedral splitting it is going to have 2 unpaired electrons. Now here one concept will come which is called as Gramos degeneracy or Gramos doublets. So that is what is also asked in question number 8, but yet I'll just explain you in short that what actually it means. Okay. So when we talk about nickel in plus 2 state, that is D8 system, in the octahedral splitting, you will be filling these 8 electrons like this. So 5, 6, 7 and 8. That's how you fill your 8 electrons. You got 2 unpaired electrons. Now these 2 unpaired electrons can have different arrangement. Either both of them can be present parallel to each other, or both of them can present anti-parallel to each other. So in this case, the spin value, the overall spin value will be half and half. So half plus half is going to give you 1, okay, and minus half and minus 1 will minus half and minus half is going to give you minus 1. So this arrangement is going to give you plus minus 1 as the as one of the arrangement, or these 2 electrons can be present like this, where you will get 0 as the I value. Okay, the spin overall spin value will be 0 over here. Now these are the 2 states which are being formed. Now like since we are not applying any external magnetic field or any external electric field yet, the ground state of this nickel plus 2 complex is going to have 2 different energy states which will be like 0 and plus minus 1, okay, because of the different arrangements possible for the electrons. So this particular system, like this particular type of splitting, is called as your 0 field, zero field splitting, or this is studied under Gramos degeneracy. Okay, Gramos degeneracy. So just look upon it that these are the two states which are possible. So the number of transitions which you will see over here will be just 1. So the correct answer for this particular question, which says that the number of EPR signals will be 1. Okay, so answer will be option number A. Alright, now let's look upon the next question. The next question says that the triatomic molecule of type AB2 shows 2 IR absorption lines and 1 Raman lines. So the structure of the molecule is. Now if the molecule is showing 2 IR absorption lines, that means there should be 2 modes which should be there and they should be IR active, and 1 Raman line, that means there should be 1 Raman active mode. Okay. Now if this is possible in a case where the molecule should have a like inversion center, then only IR modes will be Raman inactive and the Raman modes will be IR inactive. That's what is taught under rule of mutual exclusion. So according to the rule of mutual exclusion, there should be like a molecule which should have inversion center. Now we don't have inversion center in any of the options except option B. So option B is the one which will have kind of 2 IR absorption bands. What will be those IR absorption band if this is asymmetrical stretching, or if one of them is, or if you are doing a bending in this. Okay, so bending and asymmetrical stretching is going to give you IR absorption, whereas the symmetric stretching is going to give you a Raman line. So correct answer has to be option number B for this. Alright, so in order to answer this question, it says that for a tetragonally distorted chromium 3 complex, the zero field splitting result in the following number of Gramos doublets. Now Gramos doublet is one of the topic from which the question number 6 was also similar question. Okay, the question number 6 was also asked from the similar thing itself. I'll be making a separate video on this because I don't have a video on this topic on the channel, so I'll be definitely making a video on this particular topic. Okay, let me explain you that what actually happens for now over here. I guess if you have studied Gramos doublet, you will be able to answer it, but yet I'll just explain you in short that what actually is going to happen. So in this case, you are given with chromium in +3 complex, which is a D3 molecule, which is having D3 electronic configuration. So you have 3 unpaired electrons, right? You have 3 unpaired electrons. Now these 3 unpaired electrons can be either have all of them will have this spin, or they can have this spin, right? So if they have parallel or anti-parallel spin, they will have either +3/2 or -3/2. So that is the value which they will get because of this particular arrangement. Or it can happen that 2 of them are having parallel and 1 of them is having anti-parallel spin. So overall value will be like, it can be changed. Okay, you will be having this also, or it can be like this. Okay, so all these 3 arrangements will have a spin value of it can be either this will be half. Okay, so it will be plus minus half. Plus minus half you will get because over here you have this particular thing. Over here, if you see, this will have plus half spin, whereas the reverse of this can also happen, that 2 of them are below and 1 is above. Okay, or 1 below, above, below, or below then above, above. Okay, like that. So all of them are having minus half. So overall, both of them, like these 6 arrangements, can give you basically plus minus half, like plus minus half. Okay, so these are the 2 values which you will get for your for the 3 unpaired electrons. So these 3 unpaired electrons are going to give you in the ground state itself for the zero field splitting. That means when you are not applying any external magnetic field or anything. In that case also, you will be having like, there will be 2 states. One will be like plus minus 1/2 and the other one will be plus minus 3/2. These are the 2 states which are possible in it, even without, when you are not giving any external magnetic field. Okay, so when you are not giving any external electric field or magnetic field, so they are not going, you are going to get at least 2 of these energy levels. So these are called as your Gramos doublets. Okay, because they belong to 2 energy state being degenerate over here. So these are called as Gramos doublet. Okay, this is one of the Gramos doublet. This is the another set of Gramos doublet. Okay, so that means in the question they have asked you that how many for a tetragonally distorted chromium plus 3 complex, zero field splitting result in the following number of Gramos doublet. So how many Gramos doublet did you found? So we found 2 Gramos doublet, so answer would be option number B. Talking about this question over here, which says that the correct order of isomeric shift in the Mossbauer spectra of iron, okay, that's the source, and for the iron compound. So there are iron in different oxidation state. Basically we have iron in +2, +3 and +4 oxidation state. So let's write down the electronic configuration first of all. So iron in +2, iron in +3 and iron in +4 oxidation state. So for +2 it will be 4s0 and 3d6. For +3 it will be 4s0 and 3d5, and for +4 it will be 4s0 and 3d6. Now in order to solve this question, you need to understand one thing which I have already discussed on the video, in the video of my Mossbauer spectroscopy, that if there is increase in the s electron density, the isomeric shift decreases, but here the s electron density is same. We don't have to worry about that. We have to talk about the next part, which says that when the d electron density increases, your isomeric shift also increases. So isomeric shift, it increases if d electron density or the number of d electrons increases. So based upon that, you can see that sorry, it should be 4, right? It should be 4 for +4. Yeah. So based upon that, you can see that the highest number of d electrons you have in iron +3, sorry, in +2, then goes for +3, and then it goes for +4. So the d electron decreases, so isomeric shift will also decrease in this order. So the correct answer for this particular question has to be option number A, and that's how it will be the correct option. Okay. So this will give you the correct answer as option number A. Alright, let's talk about the next question, which will depend upon this particular statement which is given to us, that a 6-coordinate transition metal complex is ESR and Mossbauer active. The effective magnetic moment of the complex is 5.9 Bohr magneton. Now it says that the metal ion, along with its oxidation state and the number of unpaired electrons present are. So two things they are asking you. First of all, they have given you the magnetic moment, the effective magnetic moment, that's -5.9 Bohr magneton, and they are also talking about that which metal it should be and what it should be, like what has to be the number of unpaired electrons in that. So looking forward for each and every option one by one, we can answer this particular question. So when we have to discuss about the metal and the oxidation state, we have to see that the effective magnetic moment is 5.9 Bohr magneton. Now this 5.9 Bohr magneton is telling us that the molecule or the complex should have at least 5 unpaired electrons. Okay, there should be 5 unpaired electrons in the molecule. Now there are two things in the options, that is manganese +2 also have 5 unpaired electron, and iron in +3 also have 5 unpaired electrons, and both of them will be ESR active. Okay, both of them are going to be ESR active. Why? Because both of them contains unpaired number of electrons. So that makes both of the complexes ESR active. But the only difference is that if you look upon the transition series, in the 3D transition series, so iron, nickel and zinc, these are the only 3. Okay, iron, nickel and zinc, these are the only 3 elements of the 3D metal series which are Mossbauer active. So whenever it is given that the complex is actually Mossbauer active, so for ESR we were having both the options, but for Mossbauer it's only iron as the correct one. So your correct option for this one, for this particular one, is going to be your option number D, which says that yes, it's a ESR and Mossbauer both active. Okay, so Mossbauer both active and 5 unpaired electrons. So option number D comes out to be correct. The next question is also like question attached to the same one. It says that the complex is, now once you got that iron over here is in +3 oxidation state, and which is there in both the options, in option number B as well as in option number D. But option number B over here is a low spin complex which will not have 5 unpaired electrons. So the metal with 5 unpaired electrons and +3 oxidation state is your option number D. So option number D is correct for both of these options, both of these questions. Alright, now let's look upon the next question and the last question of this particular video. The question says that the extent of Mossbauer quadrupole splitting of iron follows the order. Okay, which order does it follows? So if you look upon the options, we have three types of complexes. These are the three complexes which we have. Let's talk about them one by one. The first one, where we have FeCl2.4H2. This 4H2 is water of crystallization, and you have iron over here in +2 state, and that too it's a high spin complex. So it's going to have a octahedral geometry because 6 ligands are there. So let's form it. So when you will fill these 6 electrons like this, you will see that neither the ligands are symmetrical over here because you have two different types of ligand, neither the electronic symmetry is there. So no ligand symmetry, okay, no ligand symmetry and no electronic symmetry. So both these symmetries are absent in this particular case. Let's look upon the other option, which is like K2, and we have FeCN5, we have FeCN5 and then NO. Okay, so here you can see that iron over here is in +2 oxidation state again. Okay, because here you will have -2, and when you will solve this, you will get iron over here in +2 state, and this +2 state is a low spin bond. So it's a low spin bond. So right now what you can see over here that it's a D6 species. When you fill it, so you will find out that 1, 2, 3, 4, 5 and 6, this is how you will fill it. So although the ligand symmetry is not there because you have two different types of ligand, so there is no ligand symmetry, okay, no ligand symmetry, but there is electronic symmetry. Okay, so electronic symmetry is there. Electronic symmetry is there because the electrons are filled symmetrically, right? The third one, which is over here, which is FeCl3 6H2. So FeCl3.6H2. It's going to be octahedral. The other three will be present as the water of crystallization. So iron over here is in +3 oxidation state. It's going to be a high spin complex. So once you will fill this, so this is how you are going to fill these 5 electrons like this. So it's a high spin complex of iron, and here you can see that the ligands are also symmetrical. Okay, you will get ligand symmetry. Okay, plus you have electronic symmetry. Both are there. Okay, so both the things are there. Ligand symmetry is also there. Electronic symmetry is also there. So we know that for the quadrupole splitting, we need that the molecule or the complex should not have ligand as well as electronic symmetry. Both the symmetries should be absent in the molecule. Then only we say that it's going to show you quadrupole splitting. So the highest quadrupole splitting you will observe in this case. Then comes your this, because here only one type of symmetry is there, the other one is absent, and here both the types of symmetries are there. So that's why the third one will be least quadrupole splitting, right? So correct option will be option number A, which says that this particular one will have highest splitting, then the other one, and then the last one. So this is how we have to solve. We were having like 12 questions we have solved on our on this particular topic of inorganic spectroscopy. I hope you guys liked the video. I hope you guys understood whatever I have taught. In the next Monday MCQ, what topic you want me to give questions from, you can ask me that in the comment section below. And if you are new to this channel, if you have not subscribed to the channel, do subscribe to the channel. If you like this particular video, give it a like. And that's all from my side for this particular video. Thank you so much for watching, and I'll see you guys in the next one. Till then, have a great day.